Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Jing Dou with us today. Hello, Jing.
Hi, Frank. Hi, everyone.
Hello. And Jing, where are you located at? What's your geolocation?
Yeah, and actually, I'm now based in Nanjing, which is in the east part of China.
Uh-huh.
It's a beautiful city, especially this season. It's spring now,
Ah,
and weather is very mild, not too cold and not too hot. So,
lovely.
yeah, and very pleasant. A lot of flowers are in bloom.
I was going to
So
ask
it's probably the best
that.
season here. And I really, yeah, love this weather and love this, yeah, beautiful thing here.
Beautiful. And it is my April 14th, 2025. It is Jing's April 15th, 2025. So we're going around the halfway around the world here. And it is spring in Phoenix, and we are also getting some flowers in the desert. And so it's very beautiful. All the yellow flowers, everything is green relative to the desert. So it's very nice, very pleasant.
Oh, great.
And
Wonderful.
Jing, what is your position there in Nanjing?
And actually, I'm now an associate researcher at the School of Astronomy and Space Science at
Oh,
Nanjing University.
cool. Congratulations. Very nice. And speaking of that position, Jing, what do you like to do for research?
My research mainly focuses on the galaxy formation and evolution, especially the star formation and quenching processes. And in particular, my collaborators and I are using large data sets such as SLON for the galaxy properties and galaxy morphologies, etc. And we also use other gas measurement, such as 21 centimeters observations to trace the atomic hydrogen, and also millimeter and sub-millimeter observations to measure the molecular hydrogen. And we also combine this observational data with some analytical models and simulations to better understand the baryon cycles in galaxies. That is how gas flows into the galaxies and form stars and expelled or quenched. And yeah, and now we are also doing some projects to study the connection between the dark matter halo and the gas content, the gas structure, etc., to better understand the galaxy evolution across the cosmic time. Yeah,
Very
basically.
cool. Very cool. And that is going to bring us to this very awesome APJ letters. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The
Yeah.
critical role of dark matter halos in driving star formation. And Jing, take us away.
Okay. Thank you. First of all, let me thank all the co-authors for their valuable suggestions and very strong support in this work, especially in Jie Peng and Louis Hu from Peking University, where I did my PhD, and also Qiu Shenggu, Yongshi, and Tao Wang here at Nanjing University,
Mm-hmm.
and also a lot of international collaborators,
Indeed.
Elvio Redani, Emmanuel Dade, and et al. So I'm very grateful to their contributions in this work. And
Good
thank you.
shout out. Good shout out. Good shout out. Okay, let's go. Dark matter halos, star formation. Here we go.
I think I will start from the basic introduction. And we know that one key question in the galaxy evolution is to understand the physical mechanisms that drive the star formation. And in the standard lambda CDM framework, the galaxies will form and evolve within the dark matter halos,
Yes.
and the dark matter halos provide the gravitational potential wheels for the gas to cool, condense, and eventually form stars. And however, the detailed connection between the dark matter halos and the baryons that drive star formation in galaxies is still an open question. So,
Yes.
Yeah, our main motivation in this paper is to study how the dark matter halo influence the baryons in the galaxy.
Okay.
And the star formation is known to link with the cold ISM, mainly composed of the atomic hydrogen H1 and molecular hydrogen H2. The H1 gas is more likely to serve as a raw material for the star formation. So it's a gas reservoir.
Mhm.
And the molecular gas H2 is mainly dominates in the denser regions and is tightly correlated with the star formation.
Hmm. Cool.
And actually, the conversion from the H1 gas to the H2 gas is a key process in the star formation. So it's very crucial and very important to understand the molecular to atomic gas mass ratio.
Yes.
Yeah. And this ratio actually is found to be influenced by many physical factors. And one of the most important is the mid-plane gas pressure.
Okay.
So yeah, the higher gas pressure actually will compress the gas, increase the gas surface density, and animate the transformation from the H1 to the H2.
Okay. Hmm.
But although there have been a lot of work about the transformation from H1 to H2, the mechanisms that govern this transition is still fully understood, especially its relationship to the dark matter halo properties.
Okay.
And we are very interested in the dark matter halo because halos, they play a very significant role in shaping the baryons in the galaxies
Oh,
because more massive halos actually they can accrete more gas and retain the gas more efficiently in
okay.
this system. But however, the specific role of the dark matter halos in regulating the star formation in galaxies is still uncertain.
Okay.
So in this study, our main goal is to study how the H2 to H1 ratio and the star formation efficiency vary with different galaxy properties, especially the dark matter halo properties. Yeah, and
Mm-hmm. Mm-hmm.
so essentially, the H1 gas is highly sensitive to the external physical processes, such as the room pressure striping and galaxy interactions. So in this study, we only choose the central spiral galaxies for
Yes.
analysis to exclude those environmental effects, including the mergers.
I'm with you.
And
Yep.
yeah, so I think basically that is the background and the motivation for this paper.
Cool.
And next, in section 2.1, we introduced how we construct our main sample in this work.
Okay.
One sample used in our work is retrieved from the Alpha Alpha survey, which is actually a large H1 survey in the local universe and contains more than 30,000 extragalactic H1 detections.
Nice.
And in order to have more additional optical properties for these galaxies, we cross-match the Alpha Alpha sample with the strong DR7 parent sample.
Okay.
And after the cross-matching, we obtain more than 9,000 reliable H1 detections in the matched sample.
Okay. Okay.
Yeah, but one thing to note that actually both strong and alpha alpha, they are both flux limited samples, which can produce very strong selection bias towards the massive H1 rich and star forming galaxies.
Yep.
So in our previous work, we have performed very careful incompleteness corrections to these samples. And so if you are interested, you can refer to Zhang et al. 2019 and Dou et al. 2024's work.
Okay.
And in brief, we assign each galaxy a statistical weight to account for this selection bias. And this weight is used in the statistical studies.
Okay.
Next, in section 2.2, we mainly introduce how we select the central spiral galaxies and the main physical properties of them. And um, after our selection, we have in total more than 4,000 central spiral galaxies, which have reliable H1 detections in this matched sample.
Okay.
And we have a rich physical properties of them. And I think one of the most critical physical quantity here is the host dark matter halo mass.
Yes.
Traditionally, people used the halo mass estimated from the abundance matching technique. But actually,
Okay.
that method assumes a one-to-one correlation
Yeah.
between the total stellar mass of the group and the halo mass.
Yes.
And it turns out that their result do not show very good agreement with the observations from the weak lensing measurements.
Okay.
And in this work, we utilized the dark matter halo mass for the galaxy from Zhao et al. 2025's work. Yeah, he is also one of our collaborator. And in their work, they developed a new machine learning technique using many observable galaxy and group properties. And I think one key feature of their approach is that they estimate the group halo masses separately for the blue and red groups
Okay.
because the quenching processes actually can decouple the halo growth and the galaxy growth.
Yes.
So
Okay.
yeah, and after the improvement, they find that their halo mass measurements is more accurate and more in excellent agreement with those measured from the weak lensing, and also in excellent agreement with the theoretical predictions and some simulations.
Nice.
So I think one innovative part of our work is that we used this new improved halo mass estimation
Okay.
compared to the traditional abundance matching technique.
Yes.
And so this improved halo mass can lead us to better quantify the connection between the dark matter halo properties and the galaxy properties.
Well, okay. I'm with you.
Yeah. So uh, let's walk through the figures and see what we find.
Let's see.
In figure one, actually we show the distribution of the central spiral galaxies on the star formation efficiency versus specific star formation rate plan.
Right here.
And
Hmm.
first, let me introduce these two quantities. The star formation efficiency, which is shown in the y-axis, actually it is the ratio between the star formation rate and the gas mass. So basically, it describes how efficiently the galaxy can turn the gas into stars.
Yes. Yes.
Yeah, and the inverse of this star formation efficiency is known as a gas depletion timescale.
Okay.
And the x-axis is the specific star formation rate,
Uh-huh.
which is defined to be the star formation rate over stellar mass. So it shows how efficiently a galaxy can resemble its stellar mass. And it also reviews the star formation activities in these galaxies or the star formation level in these systems.
Uh-huh.
So high Z bar basically means that the star formation is more active.
I'm with you.
So, and the background color represent the H2 to H1 ratio. And the grayscale of each dot marks the galaxy stellar mass. So the general trend for these dots
Or-
is that the star formation efficiency is decreasing with lower specific star formation rate. And even at a given specific star formation rate.
Okay.
you can see that the H2 to H1 ratio actually is correlated with the galaxy stellar mass.
Okay.
More massive galaxies tend to have larger H2 to H1 ratio, which means that they are more efficient to convert H1 to H2 compared to the low mass systems.
Mm-hmm. These
For
are
reference, here in this plot, we also show the star formation efficiency versus specific star formation rate for the H2 gas,
okay.
which is marked as a gray thick line.
Yes, this one. Mm-hmm.
As shown in our previous studies and many literatures for molecular gas, actually this relation is very tight. The scatter is very small and it is almost independent of other galaxy properties.
Cool.
So we name it to be the fundamental formation relation of H2, or the FFR shown here.
Mm-hmm.
So we can see that the H2 and H1 gas behave quite differently. The
Yes.
H2 form a very tight relation on this plane, while the H1 is more scattered.
Okay.
And we can also see that there are very few galaxies above this gray thick line.
Yes. It's the
And
grade up
in these
here.
regions, yes, in these regions, actually, it means that there are more H2 gas than H1 gas. So, and the depletion time scale is very short. The star formation efficiency is very high, which means that it will quickly deplete its gas.
Yep.
So this state must be unstable and unsustainable.
Right.
So it also explains why there are very few galaxies lying above this line.
Okay.
And I think this figure basically tells us that the H2 to H1 ratio is correlated with the galaxy properties,
Yes.
especially the stellar mass
Yep.
and the specific star formation rate.
Yes.
So, what is the role of the dark matter halo? This is the main question we want to ask in this paper.
Yes.
So, thanks to the improved halo mass estimation in
Yes.
figure 2,
Okay. Let's slide down to figure 2 a little bit. That was very good. Interplay, interplay, influence of the halo mass. So let's look at the halo mass. Bang. Okay.
yes. In figure 2, we show the star formation efficiency and the H2 to H1 ratio as a function of the dark matter halo mass.
Yeah.
And here we separate the galaxies into star-forming and passive ones.
Okay.
And we used different definitions. In the upper two panels, we used log SSFAR equals to -2 per gig year to separate them. And in the lower two panels, we used a more stringent criteria.
Okay.
So in this way, we are able to exclude a lot of Green Valley galaxies. So these star-forming and passive galaxies are more pure. And
Okay.
let's first look at the blue counters, which are the star-forming galaxies.
Mm-hmm.
You can see that both of the star formation efficiency and the H2 to H1 ratio will increase with the dark matter halo. Yeah, which means that
Right. I'm with
halo
mm-hmm.
has an impact on the gas conversion and the star formation in galaxies. But
Cool.
how does it work? As mentioned above, the H2 to H1 ratio is found to correlate with the midplane pressure. But
Yeah.
actually, in many studies, they calculate the midplane pressure only considering the contribution of the gas and the stars, and they usually neglect the role of the dark matter halo.
Right.
And thanks to some theoretical papers which have already pointed out that actually the dark matter halo can pour the gas onto the midplane and change the vertical distribution of the gas and stars. So in this way, the dark matter halo can indirectly change the distribution in galaxies and influence the H2 to H1 ratio.
Cool. Okay.
So here, our observation is consistent with this series. We can see that for the star-forming galaxies, more massive halos will elevate the transformation from the H1 gas to the H2 gas.
Right.
And,
Mm.
and next, let's look at the red counters,
Okay.
which are the passive galaxies.
Yes.
So if you look at the lower two panels, you can clearly find that the blue counters and red counters are clearly separated by the halo mass about 10 to 12 solar mass.
Thereabouts. Yeah. Yes, I'm with you.
You can say that passive galaxies, they were on average located at higher halo mass regions.
Right.
And actually, this is in fully consistent with the halo quenching scenario,
Yeah.
uh, which proposed that when a halo mass hit a threshold, the gas will be shock heated, and the gas accretion mode will changes from the cold mode to the hot mode.
Yes.
So actually, it will avoid the gas to further form stars and may cause the eventually quenching. So actually, our observations here confirm the halo quenching scenario.
Mm-hmm.
So for the halo mass above 10 to 12 solar mass,
Yep.
we can find that at this time, the gas accretion mode becomes a hot mode, so most of the galaxies are passive and quenched. So their star formation rate is very low. And when the halo mass is smaller than 10 to 12 solar mass, the accretion mode is still the cold mode. So there are still many star forming populations.
Cool. Yeah.
Yeah, and we can see that even at a given halo mass, the star forming and the passive galaxies exhibit very differently. So the blue counters on average will show a larger H2 to H1 ratio compared to the red ones if you fix the dark matter halo mass. So
Okay.
basically,
Okay.
it also reveals the quenching mechanism.
Yeah.
It means that for these galaxies, the H1 is less efficient to form the H2, which means that maybe there is a lot of H1 gas in these systems, but the H1 cannot form H2 because of some reasons, and that finally causes the galaxy quench. So there are still
So,
a large gas reservoir, but it cannot form the direct fall for the star formation and eventually cease the star formation.
yes. Okay. Cool.
And so this figure basically tells us that the dark matter halo is very important both for the star forming and for quench the galaxy.
Yes.
And our next question is, what's the role of other dark matter halo properties such as the halo spin or halo concentration?
Mm-hmm.
But actually, in the observation, it's very hard to obtain the measurements of halo spin and concentration. So in figure 3, we used the disk size as a proxy for the halo properties
Okay.
because in theory, the disk size is strongly correlated with the halo spin and concentration.
Okay.
The higher spin and lower concentration will lead to more extended disk.
I see.
And on the other hand, more compact halos will need to smaller disk. So in figure 3, we use the disk size as a proxy for the halo property. And
Okay.
in the other two panels, we show the star formation efficiency and the H2 to H1 ratio as a function of halo mass.
Yes.
And the color coding is the disk size.
Yes. Okay.
We can see that at a given halo mass, if we fix the halo mass,
Okay.
the both of the H1 based SFE and the H2 to H1 ratio is correlated with the disk size. More extended disk
Yeah.
will cause lower H1 based SFE and lower H2 to H1 ratio.
Put it out. Okay.
So it basically tells us that actually the halo spin and halo concentration do have some impact on the gas conversion and the star formation
Okay.
reviewed by the disk size.
Okay.
So now we find that halo properties, including its mass, spin, concentration, all have a very important role in regulating star formation in galaxies.
Okay. Very
And
cool.
and another thing is that we know the stellar mass and the halo mass is strongly correlated in galaxies, especially for the centrals. So in figure 4,
Okay.
we divide the galaxies into
Oop.
different stellar mass spins, as you can see.
Okay.
The Y and in each panel, we show the H1 based star formation efficiency versus the specific star formation rate.
Okay.
And in the upper panels, the color coding is the dark matter halo mass.
Yes. Okay.
And let's first look at the lowest stellar mass galaxies, which is shown in the upper left panel.
Mm-hmm.
For these galaxies, most of their halo mass is lower than 10 to 12 solar mass. So at this time, the gas accretion mode is still dominated by the cold mode. So
Yes.
you can see that the galaxy is still efficiently form stars.
Mm-hmm.
With the increase of the dark matter halo, you can find that both of the H1-based star formation efficiency and the specific star formation rate increase,
Yeah.
which means that at this time, the dark matter halo tend to facilitates the gas conversion and also promotes the star
Mm.
formation in galaxies.
Okay.
Yeah. So the role of dark matter halo here is to feed and sustain star formation.
That's
And for the most massive galaxies,
uh-huh.
as shown in the upper right panel,
Uh-huh.
you can see that the trend is reversed. And for these galaxies,
Ah,
most of their halo mass is larger than 10 to 12 solar mass,
yeah.
which means that according to the halo crunching scenario, the gas accretion mode has been transitioned from the cold mode to the hot mode.
Yes.
So at this time, the halo tend to become the quenching switch, which means
Mm-hmm.
that
Mm-hmm.
it will shock heated the gas and prohibits the gas to further from stars. So at this time, you can see that more massive halos tend to lead to lower specific star formation rate and also lower
Oh,
H1-based star formation efficiency,
those all have the same
which
energy.
means
Okay.
that
Good.
halo tend to be the very thing to shut down the star formation in the massive systems.
Nice.
So it basically reveals that halo actually plays differently in different stellar mass beams in
Uh-huh.
different stellar mass galaxies.
Mm-hmm. Mm-hmm.
And in the lower panels, we show
Okay.
uh, the impact of the disk size. So we can find that actually the trend is a more compact disk, smaller disk size will need to higher specific star formation rate and also higher H1 based star formation efficiency. And
Yes.
this trend actually is holding across different stellar masses. And this trend is also consistent with what we found in figure 3.
La, 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 la.
Yeah, in
La,
figure
la,
3, we found that.
yes. Yes. Okay. I see it. Uh-huh. Very good.
Yeah. And lastly, in figure 5, actually figure 5 is
Film has been.
like a summarize
Yep.
of the main points in this paper. And in this plot, we propose a evolutionary scenario. So basically, it is kind of showing how a galaxy evolves from the star-forming ones to the passive ones on the H2 to H1 versus dark matter halo plane
Okay.
across the cosmic
Oh,
time.
yes. Okay. Uh-huh.
So, at earlier times, galaxies live in low mass halos, and the gas accretion is still dominated by the cold mode, so it will efficiently form stars.
Yes.
And according to our observations before, we find that the galaxy will evolve along the blue line. So with the increase of the dark matter halo, the H2 to H1 ratio also increase,
Yep.
and the star formation is promoted.
Limit. Limit. Yes.
And um, and with the increase of the halo mass, the galaxy will reach the horizontal dash line and even enter above this line.
Uh,
And this state, actually, it is very unsustainable
okay.
because at this time, the H2 gas is larger than H1 gas, and also the star formation efficiency is very high. So the fuel of the galaxy will quickly
Yeah.
deplete in time.
Mm-hmm. Mm-hmm.
So it's very dangerous, and it is more easily to be quenched in this status. And at the same time, the halo mass for these systems have already entered the hot mode,
Right.
which proposed by the Halo quenching scenario.
Mm-hmm.
So actually,
We
the
got.
gas is shock heated and the cold gas supply is cut off.
Yep.
So yeah, it will also make the galaxy more easily to be quenched.
Nice.
So the galaxy basically will evolve along the route one, so quickly join the passive populations.
Mm-hmm.
And
All red and dead. Yep. Very cool.
also the, yeah, thank you. And also the, if you look at the peak of the blue counters and red counters,
Okay.
you may see that for the star forming and the passive ones, their H2 to H1 ratio is very comparable and very similar.
Yeah.
So it may suggest that
Mhm.
galaxy can evolve along path 3,
Okay. Yes, that's a
as shown by
possibility.
the
Mm-hmm.
one. Yeah, but actually, it's not very likely because from the peak of the blue counters to the peak of the red counters, the dark matter halo mass increase about 1 dex,
Yes.
which means that the galaxy has to be quenched at redshift about 3 or 4 because the dark matter accretion rate in the local universe is low. So, however, the observations tell us that most of the galaxies are quenched after redshift about 2. So, the route 3 is not that plausible. The more plausible routes tend to be route 1 and route 2.
Mm-hmm.
So I think this diagram basically summarized the main role of the dark matter in driving the star formation in galaxies.
Awesome.
And yeah, and about the appendix, we just show the mass star formation rate relation and the, yeah,
Mm-hmm. Getting there. Getting there. Okay. Do.
yeah,
Ba-dum-bum.
and the stator mass,
Okay.
yeah, and the stator mass disk size relation. And basically, you can see that star forming and passive galaxies, yeah, they are separated in on these two planes.
Yep, that's nice.
Yeah,
A little more overlap on this one, but okay.
yeah. And
That's just the
so I
contour.
think it's time to summarize the main points in this paper.
Okay.
Um, there are two main things I want to emphasize here.
Okay.
Uh, The first is that we used the new improved dark matter halo estimation
Mm,
for analysis
yes.
instead of the traditional abundance matching technique.
Uh-huh.
And this new halo mass actually is more consistent with the observations and theoreticals. So by adopting this new halo mass estimation, we can better study the relation between dark matter halo and the galaxy properties.
Good.
And the second thing is that uh, in this work, we emphasized the role of the dark matter in regulating star formation and the gas conversion.
Yes.
Uh, because previously, people, especially when they calculate the midplane pressure, they will always ignore the dark matter halo contribution. But actually, our observations find that uh, this contribution actually can't be neglected, and it's really important
Great.
in the star formation and quenching in galaxies.
Mhm.
So we propose a plausible halo-regulated evolutionary scenario here in this paper. And hopefully these results uh, shed some light on how dark matter interact with the gas and the star formation. And we also hope, yeah, this can motivate some further investigation for the community. Yeah.
We'll come back to that.
Thank
Very, very good. Jing, that was awesome. Very nice work. Beautiful work. Cool. Thank you so much for walking us through your very lovely article.
thank you. Thank you for having me here to
Sure.
introduce my work.
Sure. And you mentioned it a little bit there at the end. Actually, you had a couple of points as you were going through. So let me push on a little bit. And where do you think we go from here, given the published article? What are some of the next steps that one might do in this? Is there additional models to run? Is there additional data to harvest, et cetera? And so where do we go?
Yeah, actually, in this paper, we have highlighted the important role of the dark matter in regulating the star formation, but actually, the halo won't be the only player here. And recent years, there have been growing evidences that actually the AGN, which is linked with the supermassive black hole, also have important roles in regulating the star formation and quenching.
Mm-hmm.
So our next big question is how do the halos and AGNs work together or separately regulate the star formation in galaxies?
Cool.
And also, the H1 data we used in this paper is alpha alpha, but of course,
Mhm.
alpha alpha is very great, but it's not enough because it's shallow. So we can only target at the nearby H1 rich galaxies.
Right.
And next step, we are going to expand the sample to low mass and more distant objects.
Okay.
And now we have the fast telescope located in Guizhou, China.
Yes.
So yeah, and it has provided a much larger sample of the H1 detections in the
Mhm.
universe. So with them, we can revisit these trends shown in this paper and with much better statistics.
Right.
And
Very cool.
also, there are some upcoming facilities, such as the SKA,
Yes.
which can uh, push us from the global measurements to the spatially resolved observations.
That would be nice.
With the map of the H1 content, maybe we can study how the internal structure interact with other galaxy properties and halo properties and make us know what exactly happened in the galaxy systems. And also, my collaborators and I are planning to combine these observational results with some models and simulations, and also test the scenario in the model to and simulations to see how it happens and how the galaxy evolve across different cosmic time.
Yes.
So
Very good.
basically,
Cool. Very nice. Well, that'll be really exciting to see over the next couple of years as we get some more data, hopefully more resolved. We go deeper. It'll be very nice to see. So very good. All right.
thank you. Thank you.
Yeah, thank you. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye.